Okay, so given it is a clear night, I'll try not to keep it too long, so I'm sure you're eager to get outside observing. So yeah, I'm going to tell you a bit about some stuff that's close to the research that I'm doing, looking at what are known as supermassive black holes that live in the centres of most galaxies, and a bit about how they interact with those galaxies and why they're important. And I'm a theorist, and I mainly work on simulations, and this is actually an image from one of the simulations that we've done recently, capturing a region of the universe, and if we get time at the end I'll show you some of the results from this as well. But to start with, I think we'll just get on with the background. So, black holes. You may be familiar with images like this. So this is actually from the film Interstellar. And the reason I like this image is because it was created, wasn't just made up for a film, but it was created in collaboration between the filmmakers and astrophysicists. And so they actually solved the equations of general relativity around the black hole to try and get this image of what we think it would look like if we were looking at a black hole. So we see this shadow cast by the black hole, and we see this light around the black hole that's being bent around it due to gravitational lensing. And we also have this disk structure around here, which I'll talk a bit more about later on, known as an accretion. So how do we define a black hole? Well, up here I've said it's an object that's sufficiently dense, so it's an object that's sufficiently massive but also compact, that it sits within its event horizon. And so you may be saying, well, what's the event horizon of this? In essence, is the point of no return around the black hole. This is the point at which not even light can escape the gravitational pull of the central object. And if we think about a little bit about the history of where this has come from, you might think about people like Einstein, who developed the theory of general relativity, or if you've done any physics, you might think about Schwarzschild, who came up with a solution to Einstein's equation to describe a black hole. And this was in the early part of the 20th century. But actually, the idea about black holes, or objects that we think of conceptually as black holes, was being thought about way before that, back at the back end of the 18th century. So Mitchell and Laplace were thinking of objects that they called dark stars. And these are objects where the escape velocity from the surface of them is greater than the speed of light. And if that's the case, then the light can't escape, you wouldn't be able to see them, and we get this term dark stars. So let's try and put this into context. If we think about some familiar astrophysical objects, so say the Sun and the Earth, we can work out what velocity or speed you would need to have to escape from the surface, to escape the gravitational pull of these objects. And if you take something like the Sun, which you know is big, massive, it's a bit more than 16 kilometers a second. And if you take the Earth, which is much less massive, although smaller, it's something like 11 kilometers a second. Now we could turn this on its head and say, okay, if we take the Sun, we take all that mass in the Sun, and we compress it down, and make it much smaller, how small would we need to make this such that you would need to be going at the speed of light to escape from it? And if we do that, then we find the Sun would need to be about 3 kilometers across, and if we did the same for something the mass of the Earth, then it would be less than a centimeter across if it was to act like a black hole. So this is just to give you some perspective on the sort of scales we're talking about for different mass objects. Now when it comes to astrophysical black holes, they're actually broadly split into two groups. We have stellar mass black holes, which, as you might guess from the names, have masses similar to stars, and these are the byproduct of stellar evolution. So when massive stars die, their cores can collapse to form stellar mass black holes. But then, for the main interest of this talk, on the other end you have supermassive black holes, and these are black holes that are somewhere between 1 million and 10 billion times the mass of the Sun. So these are really massive objects. And these typically live, or these are expected to live in the centres of galaxies. Now, one thing I just want to mention, in my first slide when I gave the definition for the black hole, I said it needs to be sufficiently dense. So what do we mean by that? Well, if we take one of these stellar mass black holes, and we say, okay, if all of that mass is inside this event horizon, what's the average density? You get something that's about 10 to the 16s, that's 1 followed by 16 zeros times the density of water. So that's even denser than the nucleus of an atom. So this is an incredibly dense object if you have a stellar mass black hole. If we have a supermassive black hole, however, maybe it doesn't seem very intuitive, but the density, the average density within the event horizon of a supermassive black hole is similar to that of water. So actually in this case, this isn't an extreme density, it's just the fact that we have an extreme mass within its volume. Okay. So as I mentioned, supermassive black holes reside at the centers of most galaxies, and they reside at in different types of galaxies. So we can have spiral galaxies, such as this one over here, which has a black hole around 10 million times the mass of the Sun. And we have this much more massive elliptical galaxy, and right in the center here is a black hole that's about almost 7 billion times the mass of the Sun. And we've found black holes in the center of many galaxies, including in the center of the Milky Way. And actually this provides perhaps the most compelling evidence that these supermassive black holes actually exist. So this is an X-ray image of the center of the Milky Way. But over here, these points are tracking the orbits, observed orbits of individual stars in the center of the Milky Way. This was done over a number of decades to track their orbits. Try that again. And they're orbiting, and it's marked by this white star in the center here, but they're orbiting some invisible mass in the center. And based on their orbits, it can be calculated how much mass should be in here. And it's found to be a few million times the mass of the Sun. And given how tight this orbit is around this object, it's in a very small region, and it's incredibly difficult to explain it with anything other than a supermassive black hole. So as I said, this provides some of the most compelling evidence for the existence of supermassive black holes. Okay. So in the title I also talked about the relationship between black holes and their galaxies. And we actually think they have a pretty intimate relationship. They co-evolve and depend on each other quite intricately. And there are lots of observed relationships between the properties of black holes and the properties of those galaxies. So this is an example. This is called the M-sigma relation. So this is the mass of the black hole, and this is called the velocity dispersion. So it's about the speed with which the stars in the galaxy are moving. But this is essentially a proxy for the mass of the galaxy. So moving along here, you're getting more massive galaxies, and up here you're getting more massive black holes. And there's tight correlation essentially between the mass of the black hole and the mass of the galaxy. And this is essentially taken to mean that there's some close coevolution between the black hole and galaxy. So the question is, how does the galaxy know about the black hole? Now, you might think, well, we've already heard that black holes are these massive objects with strong gravitational fields, so they must be gravity, right? But the thing is, if we take the region, if we calculate the region over which the gravity of the black hole is important compared to the gravity of the galaxy, it's only important right in the very center. So essentially, if you've got something out here in the galaxy, or even here in the galaxy, gravitationally, it's not aware of the black hole, because the gravity of the galaxy, which is much more massive than the black hole. I mean, these black holes are massive, sure, but the galaxy is even more massive. So the gravity of the galaxy dominates. So, in effect, the galaxy doesn't really know anything about the black hole due to this gravity, in a direct sense. Gravity does come to play in a bit. So what is important? And how do the black holes communicate? Well, firstly, the first important thing to consider are what are known as active galaxies or active galactic nuclei. And these are galaxies, such as this one, which has a black hole in the center, and this black hole is swallowing gas, it's growing, and it's producing these jets that come out here and inflating these lobes. And so it's releasing vast amounts of energy. And so galaxies that have a black hole, it's undergoing this rapid growth phase and emitting lots of energy known as active galaxies, or active galactic nuclei. And actually it's because of this release of energy that we got the first indication, I say we, it was back in the 60s, that these supermassive black holes live in the centers of galaxies. So this here, this is a modern observation, the radio is in the red, X-rays in the blue, and some optical as well. This here is actually an early radio observation, and inside this green circle here is the first radio observation of Cygnus A here. And there's this vast amount of energy being emitted. And then in the 50s, it was found that actually this is coming from a galaxy outside our Milky Way. And this had people scratching their heads, and they had to come up with an explanation for how, from the centers of galaxies, you have so much energy coming out from such a small volume. And it's not just Cygnus A, there's a couple of other examples of a jet and a very bright, what's known as a quasar. And ultimately, it was worked out that it must be due to a black hole, a supermassive black hole. And the reason for that is that supermassive black holes are the most efficient engines in the universe, or the most efficient that we know of. Okay? So you've probably heard of this equation equals mc squared. So this is just saying how much energy is there in a particular mass of material. And we can think about how efficient different processes are for releasing energy. So if we take burning, if we set fire to some wood, then we can extract about 0.0000001% of the available energy within that wood. If we go to nuclear power, we can do a bit better. And we can release about 0.1 to 0.7%. If we go to black holes, which allow us to release what's known as gravitational potential energy, and we can get efficiencies up to somewhere between 6 and 42% of releasing the rest mass energy that's accreting or being swallowed by the black hole. So how does that work? There are a few ways you can extract energy from a black hole. And the first one, well, I'm going to talk to you about, I guess, what is the most common idea for this. So if we have a black hole here, and we have some gas cloud up here that's falling towards the black hole, you can imagine as it falls towards the black hole, it's feeling stronger and stronger gravitational force due to the black hole, it's going to accelerate, it's going to get faster and faster and faster. Now because this black hole has all this mass in such a small space, it means that this cloud can fall really fast, really far, and has lots of opportunity to speed up and reach a high velocity. Okay. And when it gets to the black hole, it ends up forming a disk around it. And this disk is orbiting, this gas is orbiting around the black hole at some large fraction of the speed of light. So this is incredibly fast that this is happening. And you can imagine that in this disk, you have all the atoms and molecules and particles, and they're all colliding with each other as they're moving around in this disk, and as they collide with each other, they heat up. So the disk heats up, and as the disk heats up, it begins to radiate. So it begins to release energy, release photons, and release light. And it's this process, so essentially you had this cloud which had what's called gravitational potential energy. As it falls towards the black hole, it loses this, it speeds up, and it's faster and faster and faster, so it's going so fast that when it forms this disk and the particles start colliding, it can release lots of energy. You've got lots of this rest mass energy of the gas in the disk into light before the material eventually falls through the event horizon into the black hole, though there's no return. And this is known as black hole feedback. So this is the production of energy through accretion. Accretion is the swallowing of the gas and its interaction with the host galaxy. And so I mentioned that there's radiation, so we have very bright regions in the sense of the galaxy. They can also drive winds. Now I'm afraid this is an artist's impression of a wind because you can't actually really see a wind when you look at a galaxy. You have to observe it through different spectral lines and shifts. But these winds can act across a large region of the galaxy, so it can have an effect on all the different scales within the galaxy. So this becomes an effective mechanism through which the black hole can communicate with the host galaxy. And then on the right here we have, as I've already mentioned, these jets. These jets are nice actually because they can actually let you see something happening within the galaxy. So these jets inflate these lobes. And if we look at things called galaxy clusters, so galaxy clusters are huge bound systems containing thousands of galaxies. So this is not going to be the Perseus cluster. And if we take a look at the very center of this and we look in the X-rays, we see these images. And X-rays, they show us hot gas within the cluster. So we can't see it in this optical image, but in between all of these galaxies, there's lots of very hot gas. And in the center here, we can see there are these cavities in the X-ray emission. And this is where these jets are actually inflating within the cluster, moving the gas about, and actually acting to help regulate how this gas is being kept hot within the cluster. So we actually see this AGM feedback in action in these black holes talking to the galaxy. Because what actually happens is when you inflate these cavities, you actually drive sound waves into the plasma within the cluster. And these sound waves can also propagate and be one source of heating of the image cluster needle. There's a number of mechanisms that are thought to be important. Now, in terms of the energy released in black holes, I already said they release vast amounts of energy. And actually what this means is that you can observe galaxies that are incredibly far away if they have a black hole that's accreting at high mass rates. So this is actually an image of one of the furthest observed galaxies in the universe. And I'm afraid it's not that impressive just to look at it here. It's actually this red dot in the center. But the light from this point in the center was emitted from the galaxy when the universe was only about 5% of its current age. So this light has traveled most of the distance of the observable universe to get to us. And the only reason we can see it is because these growing black holes release so much energy and are so bright. Okay, so for the last few minutes, I guess, I want to talk a little bit about simulations. So while we can observe AGM feedback, it's unlike other sciences in that you only get what you can see, right? You can't set up controlled experiments. With simulations, we can. So this is a simulation known as a cosmological simulation. And this is simulating a volume of the universe. And this is showing dark matter. And you can see that it's in this filamentary structure. And this is known as the cosmic web. And along the filaments, gravity is leading to clumps of dark matter to collapse and form galaxies. And now we're turning these red here showing temperature. And you can see that this is getting bright. And we're starting to see these explosions. And these explosions are actually from the central black holes in these galaxies, accreting material, swallowing material, and releasing this energy, and having an impact on the host galaxies. Actually, from these simulations, we find that the inclusion of this feedback from supermassive black holes is incredibly important to get realistic-looking galaxies with realistic properties. So, for example, we could take an image, a Hubble deep field image, looking at a section of the universe with all these galaxies in. Well, actually, only half of this is an observation. The other half is from a simulation. So let's test how good we think it is. So, who thinks the left side is simulated? And the right side? I'd say that's fairly even. it's actually the right side that's simulated. So essentially, once you run these simulations, you can take the properties of the galaxies and you can make mock observations. You can say, well, I know the properties of the gas in this galaxy, the stars in this galaxy, what would they look like if we looked at them through a particular telescope? And you can produce images like this. And you can see we have a whole range, a whole population, different types of galaxies. And the AGN feedback is important in this respect. So AGN feedback, black hole feedback, helps to regulate or quench star formation in galaxies. So if you think you have this feedback and it acts and it kicks gas out, it heats gas up. If you heat the gas up, kick it out of the galaxy, it's no longer there available to form stars. You're removing the fuel for the stars. They also regulate their own growth. If you think about a black hole, it's feeding on the gas, and if the black hole gets so big that it releases energy and pushes this gas away, it cuts off its own fuel supply. Now it could be that it pushes a little bit away and it will start growing again. On the other hand, if it's growing big enough, it could just completely kill off its own supply of food, of gas, and sit at its mass from then on. And this is one theory for how you get this M-sigma relation. And then the other thing, as I already mentioned, is that this feedback is important in getting the population morphologies of galaxies correct. So I mentioned earlier these black holes live both in spiral galaxies and in elliptical galaxies. If you didn't include the AGN feedback, it's found that you pretty much only get spiral galaxies in these simulations. So it's important to be able to get elliptical galaxies. Okay. So, what have I spoken about? So, I said supermassive black holes live at the centers of most, if not all, massive galaxies. I told you about them being incredibly efficient at converting mass to energy, giving us this feedback. And this is essentially how these supermassive black holes talk to their host galaxies. Feedback is an important ingredient in galaxy evolution for regulating black holes' growth, star formation, and also important in the galaxy clusters that I mentioned. And we perform simulations to allow us to do controlled experiments, and this black hole feedback is important. Actually, what we've got over here, this is actually a recent simulation that we've been working on to actually model in detail how these jets launched from a black hole, there's a black hole in the center here, launch and inflate these lobes, and how these lobes end up interacting with the galaxies that they live in. And we can actually see that down here, if you see this lobe, the bottom here ends up getting disrupted. And this is because there's actually some cold gas in the galaxy that ends up colliding with it and mixing this up. Okay, so I think that's everything I wanted to talk about in terms of black holes and their galaxies. Now, I know it's a clear night, so you're probably very keen to go and do some observing. So what I'm going to say is, if you want to go and do some observing and ready for that, then you can head out now. And then if anyone wants to ask any questions or have a chat about anything that I've spoken about, then feel free to stay here and we can talk about things. But I'll stop there.